Let's talk about Lewis dot structures, VSEPR bonding, all this good stuff. All right. One thing that you need to know right off the bat when we start doing this is that atoms combine to produce a more stable electron configuration, basically to achieve the full octet. They do this in one of two ways, either by sharing electrons, which we call covalent bonding, or by giving and taking electrons, which we call ionic. Well, let's handle the ionic compounds first. Okay. Ionic compounds, contrary to what you think, do not have actual bonds connecting them. So right now I have what I call the electron dot structure of our atoms. And what the electron dot structure is the symbol of the atom with a dot representing the number of valence electrons. So we know that sodium has one valence electron, that's that one dot. Chlorine has 7. So you start by putting a dot on each side of the element. We imagine that there's 4 sides. Then you double it up until there's the maximum of 2 on each side. So when sodium chlorine form an ionic bond, sorry, this should be sodium. We show this by taking the electron away from sodium and giving it to chlorine. I like to show that the electron that's being transferred as an X. That way I keep track of who the original electrons are and who the one being accepted is. And if you see, there's nothing really attaching these two atoms together except for an electrostatic attraction. We can visualize ionic compound as being in like a suspended lattice structure, like 3-dimensional cube, where you have some sodium and some chlorine, sodium, chlorine, kind of all stacked upon each other in a 3-dimensional array. The formula that we achieve, the NaCl, is really the ratio based on the charge balance, which we went over when we talked about naming and forming ionic compounds. But for the rest of this chapter, we're going to focus on covalent compounds. And when we talk about covalent compounds, we learn how to demonstrate or illustrate how these electrons are shared with each other. So let's get some terminology straight before we do anything. If we say that there are electrons being shared between atoms, those are known as bonding pairs. If there are electrons not shared, they are called lone pairs or non-bonding pairs. So let's look at a structure of water. So if we have our oxygen atom, oxygen has 6 valence electrons. So we're going to go 1, 2, 3, 4, 5, 6. Therefore, oxygen has 2 lone pairs here and there. And it has 2 electrons that can form a bonding pair. It just so happens that in the structure of water, hydrogen also only has 1 electron available. So they create a bonding pair. Same thing here for space. I'm going to make it really sloppy, but it looks something like this. So that the electrons being shared are the bonding pair, and the ones that are originally on there from the Lewis structure is known as the lone pair. Now, it's also important to know that there are different types of bonding pairs that we can have. We can form a single bond, a double bond, or a triple bond. When we say it's a single bond, it's 1 electron shared from each atom. If it's a double bond, it's 2 electrons shared from each atom. If it's a triple bond, then it's 3 electrons from each atom. And it's important to note that we can use more than 1 single bond to fill an octet. So let's look at examples here of hydrogen, oxygen, and nitrogen. Okay. So the first thing you do is we start by drawing the Lewis structure. So we have hydrogen with 1 electron, and we have another hydrogen with 1 electron. Hydrogen likes to follow the duet rule, so it's only going to want to have 2 electrons, and they achieve that by sharing it together. They're now happy. Oxygen has 6. 1, 2, 3, 4, 5, 6. And we have 2 of them. That's what that 2 means. 1, 2, 3, 4, 5, 6. So oxygen has 2 lone pairs. We're not going to touch them. Then these bonding pairs will connect, and these will connect to form a double bond, so that the final structure will look like this. Next, we have nitrogen. Nitrogen has 5 valence electrons. Okay, so we have 2 atoms of nitrogen. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And no, this is about where the students start to ask, does it matter where you start? Nope. I just know from doing this for so long, to make the illustration a little bit clearer, I know where to place the lone pairs of electrons. So looking here, we know that these guys are going to bond. We know that these guys are going to bond. And we know that these guys are going to bond. These lone pairs are going to stay out of it. Now, just looking to see if it's following the octet rule, we have 2, 4, 6, 8 shared electrons. 2, 4, 6, 8 electrons. Both nitrogen atom is happy. And we can write the final structure like that. That's how we write the electron dot structures, and it's the beginning of how to write Lewis structures. Okay. So while we have ionic compounds and we have covalent compounds, there are also 2 categories of covalent compounds, and that's because elements have different types of electronegativity. So what is electronegativity? Electronegativity means that there are some atoms who want the electrons more, and we know that these are the halogens and everybody closer to that, achieving that octet. Okay, so we say that those type of atoms that have a difference in electronegativity are polar covalent compounds, meaning that one atom is going to pull the electron closer to its side, but not completely making it separate like an ionic compound. So I'm going to give you a very generic example of hydrogen fluoride. Hydrogen is not as polar as fluorine based on the electronegativity values. So that when hydrogen and fluorine bond, fluorine actually pulls that shared electron closer to it so that the electron density is greater by the fluorine. And we can show this by what's called a dipole, which shows the flow of the electronegativity or the polarity. So that way the arrow shows where the more polar atom is, and this end shows where the least polar is. So it can show the flow or the pull of the electrons. That's known as a polar covalent compound. Nonpolar covalent means that atoms have a small to no difference in electronegativity. They share electrons equally. Normally they're symmetric. So say the O2 molecule, CH4, CCl4, BH3. Notice how they're all surrounded by the same. There's no real pull and there's no dipole. One of the exceptions to this is carbon dioxide. Okay, carbon dioxide is a nonpolar compound. However, it has a dipole, has 2 dipoles, because the oxygen is more electronegative than carbon. Generally speaking, electronegativity tends to increase as you move towards the right side of the periodic table, and it decreases as you move down. A good indicator is to know that fluorine is the most electronegative element, francium is the least, and of course the noble gases don't have an electronegativity value because they don't want to gain or lose electrons. They're happy the way that they are. Okay, guys. Oh, hold on one second. Find my webcam. Okay. So here are the rules for writing the Lewis structures as we start to get into the practice with it. The first thing is that you are going to calculate the total number of valence electrons within that formula. If it's an ion, you're going to add in the electrons. If it's a cation, you're going to subtract the electrons from the total. Then you're going to write the skeleton structure where hydrogens are on the outside and the more electronegative elements are on the inside. You're going to distribute the electrons by starting with the outside and working in towards the central atom. If you end up with extra electrons, put them on the central atom. And don't underestimate being able to make double and triple bonds in order to fulfill the octet with the central atom. So I'll give you a second, or you can pause this to write this down. Okay. And this helpful rule is something that my husband actually showed me. It's called the HUNK 1, 2, 3, 4 rule, meaning that the hydrogen and halogen elements can form 1 bond, oxygen can form 2 bonds, nitrogen can form 3, and carbon can form up to 4 bonds. That's including single, double, and triple bonds. This does not include their non-bonding the lone pairs of electrons. So hydrogen will have no lone pairs. The halogens will have 3 lone pairs. Hydrogen will have 2 lone pairs. Nitrogen will have 1 lone pair. And carbon, we'll say it shouldn't have any, but there are exceptions to that rule. So let's start with doing some examples. So the first, I've already showed you some. So let's start with NH3, ammonia. Okay. Nitrogen has 5 valence electrons, and you have hydrogen, which has 1, but there's 3 of them, so that's 3. So we have a total of 8 valence electrons that we need to account for when we make this bond. We said that hydrogen goes on the outside, so nitrogen is going to go on the inside. So we're just going to arrange the hydrogens around the nitrogen, and we're going to make the bonds. Each bond represents 2 electrons, 2, 4, 6. So 8 minus 6 leaves us with 2 electrons left. And since there's 2 electrons left, we said we're going to put them on the central atom. That is the Lewis dot structure for ammonia. Double check. All of the hydrogens fulfill the duet rule. They're completely full. And the nitrogen has 2, 4, 6, 8 electrons, 3 bonding pairs, 1 lone pair. Okay. Let's try another. All right. Let's do OF2. Okay. Oxygen has 6. We have 2 fluorines, so that's 14 because they have 7 apiece. That's 20 electrons total. Now, I know I said that we are going to put the most electronegative elements in the center, but fluorine can only bond 1 time. So it has to go on the outside. Oxygen has to go in the center. So we can put the fluorines around the oxygen and bond it 1 time. Okay, now let's look at those outer atoms. Fluorine does not satisfy its octet rule, so let's add electrons around so that way it does. So you're going to add 1 lone pair, 2 lone pair, 3 lone pairs on each. Okay, now the fluorine's happy, and we've used a total of 2, 4, 6, 8, 10, 12, 14, 16 electrons. So 20 minus 16 is 4. Where are those extra 4 electrons going to go since these are completely filled? 1, 2, 3, 4. Next, NF3. Okay, nitrogen has 5, fluorine has 7 times 3 is 21. So 5 plus 21 equals 26. Nitrogen goes in the middle. We're going to surround it with fluorine. And we're going to add those electrons for the lone pairs to complete the octet for fluorine. So that's 2, 4, 6, 8 times 3. That's 24. And we have 2 electrons left that we're going to put on the central atom. Okay, let's crank this up a notch. NH2OH. Oh no. Let's look at those 3 elements. Here's a hint. When you have a structure like this, generally, if the H's are next to that, they're bonded to that atom, and that hydrogen would be bonded to oxygen. It gives you a hint of how you're going to arrange the skeleton. So we have 5 plus 6 electrons, that's 11, plus 3 is 14 total electrons. All right, so our nitrogen is going to have our hydrogens, and our oxygen is going to have our hydrogen. And so therefore, these two must be bonded together. Let's see how many electrons we've used. 2, 4, 6, 8. Okay, so 14 minus 8 is 6. So let's put 2 electrons on nitrogen. 2, 4, 6, 8. Nitrogen's happy. So that's minus 2 more. So now we have 4 left. Where are they going to go? They're going to go on the oxygen. 2, 4, 6, 8. Everybody wins. Also, you're following the octet rule, the honk rule. Okay. HCN. 1 plus 4 plus 5 is 10. And again, look at how it's arranged. So we know that the hydrogen is going to be bonded to the carbon, which is going to be bonded to the nitrogen. So that takes care of 4 electrons right there. That leaves us with 6. What can we see right now? Well, let's put 2 on the nitrogen and see what happens. So that takes away 2 more. That leaves us with 4. Well, gosh, now what? We know hydrogen's good. Nitrogen needs 2 more, or 4 more electrons, and so does carbon. So what we can do is we can do 1, 2, 3, 4. I will tell you, sometimes it takes trial and error. So you might want to use a pencil when you're trying these. Now we know that nitrogen can make up to 3 bonds. We know that carbon can do 4. Use the honk rule to help you. Okay. Last one. NO minus. Ho, ho, ho. Now what? All right, so we've got 5 and we've got 6 plus 1 electron. So it's 12 total. 5 plus 6 plus 1. So we've got our nitrogen that can make 3 bonds and our oxygen that can make 2 bonds. So let's give them 1 bond right off the bat. Let's give our nitrogen 2 electrons. So that's going to give us 8 left to arrange. So nitrogen can make 3 bonds. Let's just put them there and them there. And that's 4, 5, 6, 7, 8. But that doesn't make any sense, does it? No. All right, so let's try this again. We have our nitrogen. Bonding with our oxygen. And we'll do that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Does that work? 2, 4, 6, 8. 2, 4, 6. It's 2, 4, 6, 8, 10. So we're short, so let's do this. 2, 4, 6, 8, 10, 12. 2, 4, 6, 8, 2, 4, 6, 8. Everybody's happy. And that is the conclusion on how to write Lewis structures. Okay, all that's left is learning how to draw resonance structures, which should come after you practice doing Lewis structures, and I believe formal charge. And then we get to VSEPR. So I'm going to save that for another time. Maybe I'll just do a resonance right now. That way we can just finish this part up. Now, what is a resonance structure? A resonance structure means that the electrons can bond in more than one way. Okay, so if we have something like ozone, which is O3, okay, so here we have 3 oxygens. Okay, and then this is the structure of ozone. Okay, so it doesn't exactly follow the hunk rule, but like we said, sometimes you have exceptions to make it work. The thing is with ozone is that it could be this structure or it could be this structure. We don't know where those electrons are that make the double bond. So it could be this or this, when in reality, it's really a mixture of the two because the electrons from this double bond can flip sides. And so that's what we mean by a resonance structure. Typically, we see resonance structures when we have a double bond with oxygen. And we see this a lot with our polyatomic ions like sulfate and nitrate and phosphate. And so that's what we mean by resonance structures. Okay, so if I show you the resonance structure for nitrate, which is NO3 minus, okay, nitrogen is in the center. We have oxygen, oxygen, oxygen. 1, 2, 3, 4, 5, 6. Okay. Then we have 2, 4, 6. 2, 4, 6. Okay. And we generally show that extra electron that's there for the structure. A question that I get asked often is, where does that electron come from? It comes from the environment around. It comes from somebody giving or taking the electrons. And that electron is necessary to complete the octet to make it stable. And so what happens with the resonance structure is that this double bond kind of makes its rounds. So that the actual structure is somewhere, it's a mixture of these three structures because of the movement of the electrons. Which brings up the question of, how do we know which one is the preferred structure? So if we want, we can use something known as formal charge. And so formal charge is a formula. Okay. And you want to have the one that has the Lewis formula that doesn't have charges on adjacent atoms. So how do we calculate formal charge? Formal charge is equal to the number of valence electrons in the unbonded atom minus the unshared electrons plus half of the shared electrons. So we're going to do this for H2SO4. So we're going to write out the two possible structures for this. And it's going to be HOSO, HOO, and filling in the electrons. So which one is it? So let's take a look at this one first. The formal charge is equal to the number of valence electrons in the neutral unbonded atom minus the number of unshared electrons plus half of the shared electrons. So we're going to do it for H first. Okay. So how many valence electrons does this hydrogen have? Okay. Hydrogen has 1. How many does it have bonded? 0. Oh, sorry, unshared electrons has 0. And then half of shared is 1, which means that the H has 0, has a formal charge of 0. Now the oxygen, we're going to deal with this oxygen. It has 6 valence electrons when it's unbonded. Okay. Now the number of unshared electrons 1, 2, 3, 4. Those are not shared. Those are the lone pairs. And you want half of the shared. So it's sharing 4, which is 2. And that also equals 0. Let's do sulfur. Sulfur typically has 6 valence electrons. It currently has no unshared electrons. And half of the shared electrons would be 4 because it's sharing 8 total. And that gives it a formal charge of 2. And yes, you do this for all of the different types of elements in the compound. Let's do these O's right here. Oxygen has 6 valence electrons. It has 6 unshared electrons. And it only has 2 that it's sharing, plus 1. And that gives it an overall formal charge of -1. Okay, so that on this compound, this has a formal charge of 0. This has a formal charge of 0. The sulfur has a formal charge of 2. This oxygen has a -1. This oxygen has a -1. This has a 0. This has a 0. So overall, the overall formal charge for this compound is okay. However, if we look at this formal charge, we know that that's going to be 0. We know that that's going to be 0. So we're only really looking at this sulfur and this oxygen because these are all the same. So let's look at the sulfur. Sulfur has 6 minus sorry, I lost my spot. Okay, so it's sharing 8. So we're going to have half of 4. And how many unshared electrons do we have? None. Everybody's being shared. So 6 minus 4 is 2. That's not right. Oh, see, silly me. I missed those ones to the oxygen. 6 unpaired minus 0 plus 1, 2, 3, 4, 5, 6. That's 12, so 6. So that equals 0. And then here's our oxygen. We're referring to these oxygens here. Oxygen has 6. It has 4 unshared plus 2 of the shared, and that equals 0. So which one of these has the lowest formal charge? Because that's the most probable. It'd be the one that has 0, not +2 and -1. Okay. And that's where I'm going to stop, except for Vesper. I will do Vesper another night and give you some resources on that. This gets us through, I think, to pretty much the end. All right.